Hey, I'm Cameron Kimber. I think for now it's best if you call me Teacher Cam. And welcome to physics class. I went to college in the United States to learn more about physics, and I hope to go back in the future to learn more about it. My goal in this class is to convince you, as I believe, that physics is probably the most interesting things the human mind has put itself to in all of history. Although, personally, I believe music is a pretty close second. Just what is physics? I think if I had to tell you an answer, a succinct answer, I would say that physics is the qualitative study of the interactions of matter and energy. The quantitative study of the interactions of matter and energy. Quantitative, in that it tries to find numbers, to find relationships between the interactions of matter and energy. Quantitative, quantities, numbers. What then are matter and energy? I think for now, the best definition I can give you is that matter is just stuff. You and I are made of matter. The sun is made of matter. The nearest 7-Eleven is made of matter. The air that we breathe is matter. Quarks, protons, neutrons, electrons, all that stuff. All that stuff is matter. What's energy then? The textbook definition of energy is the ability to do work. Not work like swinging a hammer, or working at the grocery store, or cleaning the dishes. But work is in applying a force to an object across some distance. Boiling water, lifting heavy things off the ground, propelling a rocket into space, and shooting a basketball towards a hoop. Stars going supernova. All these things require energy. Physics is the quantitative study of the relationship between matter and energy. But just how do we do it, and what does it entail? Does physics require you to memorize a bunch of stuff? Does it require you to know a bunch of mathematics? I want to tell you two stories. Two stories that are divided by about 2,000 years in time. Of people doing physics simply by paying attention and being very curious. The first of these stories is about a man named Eratosthenes, who was born in 276 BC in a city in modern-day Libya called Cyrene, in the Greek Empire. He was a Greek polymath, a mathematician, a geographer, a poet, an astronomer, and he also liked music theory. He was a man of learning, and he became the chief librarian at the Library of Alexandria. His work is comparable to what now we call geography. Eratosthenes was the founder of scientific chronology. He endeavored to revise the dates of the main events of the semi-mythological Trojan War, dating to the sack of Troy in 1183 BC. In number theory, he introduced the sieve of Eratosthenes, a method of finding prime numbers. He was a figure of influence in many fields. According to an entry in the Suda, a 10th century encyclopedia, his critics scorned him, calling him beta, because they thought that he was the second best at everything, not the best at anything. Nonetheless, people like to call him Penthelos, after the Olympians who were well-rounded competitors. He had proven himself to be knowledgeable in every area of learning. Eratosthenes yearned to understand the complexities of the entire world. On to the story. As chief librarian of the Library of Alexandria, Eratosthenes had access to records and books from all over the empire. In one, he read a strange account that stuck with him and led him to discover something amazing. At noon, when the sun was directly overhead, on the longest day of the year, in the city of Sine, you could look down into the bottom of a well and see the sun reflecting back up at you. Eratosthenes waited until noon on the longest day of the year in Alexandria. Instead of looking into a well to see the sun reflected at him, he measured the shadow from an obelisk, a type of rock that sticks out of the ground, a type of stele that they would build in Egypt at the time. He measured the shadow. If the sun were perfectly overhead, as it were in the story, the obelisk would cast no shadow. Eratosthenes reasoned that the story in the book still had to be true. Who would lie about it? And so was the shadow that he saw from the obelisk. He saw it himself. The only way this could be possible, he thought, is if the earth was curved. Using the shadow, he calculated the angular distance between Sine and Alexandria to be 7.2 degrees. At the time, surveyors from the empire walked from city to city to make maps, and Eratosthenes paid one of them to measure the distance between Alexandria and Sine. Let's cut to the classroom, take a look at the chalkboard to see the results that he got. Here we have the Earth. As you can see, the North Pole is actually tilted back a little bit, which means that the equator is tilted up a little bit from the rest of the plane of the solar system. Now, Eratosthenes read an account when the sun was directly overhead in Sine on the longest day of the year, which would mean that Sine lies here, about 23.5 latitude, which we call the Tropic of Cancer, which is the day where the sun is as high in the sky as it's going to go in the northern hemisphere. As you may know, the axial tilt, the Earth being tilted away from the sun, is what causes us to have seasons. It makes days longer in the north during summer and shorter for us in the northern hemisphere when it's summer in the southern hemisphere. Now, Eratosthenes lived in Alexandria, and he read about somebody who lived in Sine. Like I said already, the sun was directly overhead in Sine. You could look down into the bottom of a well and see the sun right above you. So Eratosthenes went out and looked at the shadow from an obelisk in Alexandria, and he measured that the angle of the sun over the obelisk must make about 7.2 degrees. It was not exactly 0, it was about 7.2 degrees. So from there, he did a little bit of simple trigonometry. Here's the triangle that he had. This is the radius of the Earth right here, and this is the distance between Sine and Alexandria, which, again, he knew because people were making maps of the kingdom, would be 5,000 stadia, 5,000 Greek stadia. We don't use that anymore, but now we use kilometers. We know that the sine of an angle is the opposite over the hypotenuse. And look, here we have the opposite, and here we have a hypotenuse called r. And we have the angle theta here is 7.2. So if we plug that in, sine of 7.2 is going to be equal to 5,000 divided by the hypotenuse, divided by the radius of the Earth. We can rearrange it to solve for r, and that's what we've got here. The radius of the Earth is equal to 5,000 stadia divided by sine of 7.2, which gives us 39,893 Greek stadia. Now, the circumference of a circle is 2 times pi times r, 2 times pi times r. And we've got that here. If you plug in the numbers and run it, it gets you 250,659 Greek stadia. It's less than 1% away from what we actually believe it is now. Eratosthenes got the right answer using the sun, some shadows, some people walking back and forth between cities. Pretty amazing. Our next story is going to take us to America in 1964, where we meet Arno Allen Penzias and his partner Robert Woodrow Wilson in their workplace, Bell Laboratories, named after Alexander Graham Bell, the creator of the telephone. The two were working on wireless intercontinental communication, talking to Europe on the phone without the need for a phone wire. They had built their most sensitive radio dish yet. There was only one problem. No matter where they pointed it, they kept getting this constant, strange radio noise that they couldn't get rid of. First they thought, maybe it's coming from New York City. That wasn't right. As it turns out, New York City's only in one direction, and it wasn't even fitting with the model that they had created. So they go out and they troubleshoot. They check their instruments, and they find that it's covered with pigeon crap, pigeon droppings and bat droppings. So they scrub it clean. They actually take up all the pigeons they can find, load them into the car, and drive them about 100 kilometers away. The only problem is these were homing pigeons, and by the time they made it back to the lab, the pigeons had beaten them all there and made their roosts back in the satellite dishes as they were before. They then got in touch with an astrophysicist named Robert Dicke, who proposed that maybe this could be the background radiation of some cosmological models that had been proposed at the time. The three of them agreed to publish letters in the Astrophysical Journal. Penzias and Wilson would publish their data, while Robert Dicke would publish his interpretation of the model. Penzias and Wilson, in working on wireless intercontinental communication, had discovered something amazing. the echoes of the creation of the universe. Just like in the story of Eratosthenes, all this took was curiosity and attention to detail. And just like Eratosthenes, the results of this happy accident changed the way that we look at the world for forever. I've had a nice time out here. Let's go back to the classroom for the rest of the day. Now, given the examples that we've seen, and what you may already know about physics, it's going to be important that we have some units of measurement, some standards that we compare other things against to say how big they are, how far away they are, how heavy they are, how long of a time we talk about. And in the international physics community, we've agreed on using a system we like to call MKS. It's a decimal system, so we're going to multiply these or divide these by 10 when we need to. The unit of length is called a meter, and we just write a little m for that. The unit of mass is called a kilogram, and we write kg. The unit of time is called a second. This is the fundamental, the base unit of time, and we like to write s for it. So again, MKS, meters, kilograms, seconds. Now sometimes it doesn't always make sense to talk about things in MKS. For example, if you're talking about the distance from the Earth to the Sun, it's hard to imagine that it's so many of these, about a meter away. You need to talk about a bigger thing than that. Or if you're talking about nuclear physics, where you want to know how long it takes a photon, a particle of light, to travel across the radius of an atomic nucleus or something, well, it turns out that a second is about an eternity to something like that. And so they talk about time in femtoseconds and picoseconds, tiny little fractions of a second, trillions of a second, or smaller, quadrillions of a second. There's another form of units called CGS, and we'll just touch it really quickly. Centimeters, grams, seconds. As you can see, centimeters are just hundreds of meters, grams are thousands of kilograms, and seconds are the same. And so CGS is pretty popular in the astrophysics community, even though they deal with bigger stuff. I don't know why they use CGS. Now there is this bracket notation, as you can see here. I have time, I have it in little brackets. I have mass, I have it in little brackets. This is what we write when we want to say what are the units of this. And so I want to give you an example really quick. I'll give you two examples. One that you probably already know, and another that you don't know. Now think about it. You're driving in your car, or you're riding on a scooter, and it's got some number there. It tells you how fast you're going. What are the units of speed? Well, let's try it. We're going to write speed, and then we're going to write it in these brackets, so we can tell that what we want from this is that we want to know what the units are. Speed is going to be equal to, and you may already know this, length divided by time. And so the units of speed are going to be the units of length divided by the units of time. So maybe meters per second, maybe centimeters per second, although your car or your scooter is probably going to tell you kilometers per hour. I'm from America, where we don't know what a kilometer is, and so we talk about things in miles per hour, or maybe feet per second, but that's how it goes over there. I'm going to tell you another unit of measurement, one that we'll be fairly acquainted well with before too long, and that is the unit of force, how hard you have to push something to make it move. So let's see, force, I'll write it again in brackets, force. Well, the units of force are going to be the units of mass, so mass, and then times the units for acceleration. Acceleration is how much faster you're getting, not how fast you're going, but how much faster you're getting per time. So that's going to be meters per second squared, or length per time squared. So mass times length divided by time squared. And in MKS, the unit for force is called a Newton, after Isaac Newton, who again we will learn a lot about this semester. Overall, the universe spans about 45 orders of magnitude. When I say that, I mean from the smallest atoms, from the smallest particles that we can detect,
into the size of the scale of the universe, you'd have to take this and multiply it by 10, and then multiply it by 10, and multiply it by 10, and multiply it by 10. And if you multiplied it by 10 about 45 times, you could go from the size of the smallest particles we know to the size of the entire universe. So now I want to show you a quick video on the orders of magnitude, just so you can begin to think of the scale of the problems that we like to deal with in physics. You know, we like to deal with both the very small and the very large, so I think this video is a good way of trying to understand the differences between how small some things can be and how big some other things can be. Overall, the universe scales about 45 orders of magnitude, which means factor of 10, 45 orders of magnitude. So that means if you took the smallest particles we knew, and you multiplied their size by 10, and you multiplied that by 10, and you multiplied that by 10, and so on, 45 times, you would go from the size of the smallest particles that we know about to the size of the entire universe. So I want to show you a video now that shows you the different orders of magnitude that we're aware of in the universe and the scale of the problems we like to deal with in physics.